Welcome back. In last couple of lectures, we discussed about chemical shifts, one of the most important NMR parameters which arises because of internal interactions. That was interaction of the nuclear spin with the magnetic field, which is because of the electronic environment surrounding it, which shields the nucleus. And we understood a lot about chemical shifts, what happens to it with the magnetic field, and what is the difference between the ppm and chemical shift scale, and various things, and the factors that influences chemical shifts. Everything we understood. I hope you are all with me. Today I am going to discuss another very interesting NMR parameter which is responsible for understanding the multiplicity of the NMR signals, which tells you what is its next nearest neighbor and subsequent neighbors, like that. And this helps in assigning and getting the structural information, conformational information of the molecules. This is one of the very important things to find out. If I'm looking at a proton, I want to know what is the next functional group sitting next to it or covalently bonded to it. So that type of information very easily we can derive by understanding scalar couplings. Okay. Before that, let me tell you, the NMR spectrum has many components. First of all, if you look at the NMR spectrum like this, which I said how to get the resonance in the couple of lectures before, look at this one. This is the shape of a peak. There are several information which is content in this. First thing, the position of the peak. That's what we have been discussing in the last couple of classes. That is what is called chemical shift, with respect to some reference which you use in a particular nuclei of observation. What is the position? For example, in proton, with respect to tetramethylsilane, what is the chemical shift position in frequency or ppm of a particular peak? So peak position is important. Second, area of the peak. I told you, remember, area of the peak gives you the number of protons present in that relative to other one. Okay, I have to have some reference, some peak. If I know what are the number of protons present in that, with respect to that relativity with the peak height, I can find out, I can tell you what are the number of peaks present in that. For example, if it is a CH3 group, if I know where is the CH group, I know CH group comes because of single proton, then related to that I will say this intensity must be 3 and this should have 3 protons. Like that, peak area tells you, identify the number of nuclei, number of spins or number of protons which are responsible for this. And another interesting thing what we have to discuss from today's class onwards is the multiplicity pattern. This peak, assuming there are no other neighbors which are interacting with it, with this it is going to be a single peak. Assuming I am looking for a proton in a molecule or a hydrogen where it is resonating, if I look for the chemical shift of it, if all the neighbors are far away and there is no interaction of other protons or any other NMR active nuclei with this particular proton of my interest, it will be a single peak. If it starts interacting, then this peak starts giving rise to multiplicity. It starts undergoing splitting and we get multiplicity pattern. The multiplicity pattern can be different types, various types. It could be 2 lines of equal intensity, or it could be 3 lines of equal intensity. It could be 3 lines of different intensity, like 1:2:1. Varieties of things happen. So that multiplicity pattern tells me what are the neighboring interacting spins. Okay, what are they and how this is split because of them. Second is line width and shape of the peak. The shape of the peak and line width also gives me sometimes dynamic information. If it is let us say I have 2 peaks, assuming that I have taken an NMR spectrum, one peak is very sharp, other peak related to that is very broad. This has an information content. It tells me why this peak is broad. It is undergoing fast relaxation, or it may be undergoing some dynamics. It may be undergoing exchange. So some dynamics is going on in this proton. As a consequence, it is relatively very broad compared to the sharp peak. So it gives me information about the dynamics of the molecule. So NMR peak has several information present. So now we have to understand. First, we understood the peak position in the last couple of classes, that is chemical shift, where it comes with respect to a reference. Now we also understood the peak area, which tells us the number of protons which are responsible for that peak. Today we will understand multiplicity pattern, how the neighboring spins will interact with the proton of my interest, and how the multiplicity arises. Of course, as a consequence, we also understand later about the dynamics, how the line width and shape of the peak gets affected. Okay, with this information, let us start discussing about spin-spin coupling. As I said, remember, except quadrupolar interaction, all are magnetic interaction. It is the magnetic interaction of the two nuclear spins. Okay, let us say this is one nuclear spin, this is another nuclear spin. There is a magnetic interaction between these two with involvement of bonding electrons. Remember, there must be a covalent bond between these two. With the involvement of a bonding electron, the nuclear spin here transfers its polarization or magnetization to this, or this can interact with this. So as a consequence, the polarization is transmitted through covalent bond. For that, the medium is bonding electron. That is necessary. Remember, this nuclear spin can see this one through covalent bond. If that is the idea, what is the mechanism? How this nuclear spin, one nuclear spin, sees the other nuclear spin? How do they interact? One of the dominant interaction mechanism is what is called Fermi contact interaction, Fermi interaction. This arises because of bonding electrons. Remember, the Fermi interaction is there. That is very, very important. And we will start by taking an example of a one single CH bond. Here, carbon 13 is an interacting spin. Carbon 13 has a spin. It has spin half. Proton has spin half. I'll take the CH bond. So when both are having spin half, both are tiny magnets, I said, they will interact. The nucleus of carbon, the nuclear spin of carbon can interact with nuclear spin of hydrogen. In other words, the magnetic moment of this carbon can interact with the magnetic moment of this hydrogen, this proton. Now, it must be connected by a sigma bond with having two electrons. That's what CH bond we are considering. When we consider CH bond, it is connected by a single sigma bond. Okay. And I am isolated CH bond I am taking. Forget about what other things are attached to this carbon, this proton. I'm not bothered. Just for understanding purpose, I am taking a CH bond. It has a single sigma bond with two electrons. That's well known in the chemistry. Now we will start looking at one of the nuclei, either carbon 13 or proton, doesn't matter. You can take anything you want. Let us consider, I'll take the hydrogen atom. Now, moment I put the nuclear spin in a magnetic field, what are the possible orientations? The magnetic moment of this hydrogen has two possible orientations because it is spin half. As a consequence, there are two possible orientations for this magnetic moment. One in the direction of the field, other in the direction opposite to that of the field. Please understand. Now, the magnetic moment of hydrogen has two possible orientations in the magnetic field. With that idea, let us start further, go further. Let us take the ground state orientation of the proton. What is the ground state orientation? Which is alpha state, which is parallel to the field, lower energy. We'll consider alpha state, which is orientation of the proton parallel to the field, which has lower energy. Now, what is the energetically preferred state for this magnetic moment? Now I'm considering nuclear spin, proton coupled to carbon with a sigma bond where there are two electrons. The energetically preferred state for this magnetic moment is the orientation of this should be anti-parallel to the magnetic moment of the nearest bonding electron. Please understand this statement. The orientation of this proton, now I am considering proton with the ground state of the proton with the orientation parallel to the field. That is the lowest energy configuration. I said that is the lowest energy option for this. The spins with the orient parallel to the field, the lowest energy. That's what we have been discussing from the day one. For this to be energetically in a preferred state, the electron which is attached to this, which is forming a bond, must be anti-parallel to this. If this is the orientation of the magnetic moment of proton, the electron magnetic moment should be anti-parallel to this. This is the preferred orientation. This is the minimum energy configuration for this. That should be there. Now let us see the drawing, how it orients. Diagrammatically we'll try to understand. I have drawn a crude diagram myself. Don't worry about it. Drawing may not be very good. I'm not a very good artist. Doesn't matter. Look at this proton spin. I have taken it to be in the direction parallel to the magnetic field, lower energy. Only one component of this magnetic moment, which is in the direction of the field I take. Now the Fermi contact tells me, because of that, this electron has to be anti-parallel to this. That is the preferred energy state. But the question is, why did I write parallel to this? Remember, even though I have written diagrammatically like this is lowest energy for this because electron has a negative magnetic moment. Please understand, electron has a negative magnetic moment. As a consequence, even though these two are parallel, there is a minimum energy. It is as good as telling this electron is anti-parallel to orientation to this proton magnetic moment. Please remember this point. That is why diagrammatically I have shown this to be in a parallel to this magnetic moment because of electron has a negative magnetic moment. Okay, so far so good. Now what is the next one? Look at the other electron, bonding electron. There are two electrons in the sigma bond. Now you understand the Pauli principle. What does it Pauli principle say? These two electrons should be paired. The two electrons between these two must be, bonding electron must be paired. So when this is in the direction parallel to the field, this must be opposite to this electron. I know because of this orientation parallel to the field, I know what is the orientation of this electron, and as a consequence, I know orientation of this bonding electron. Now, when this is like this must be opposite to this electron. But I represent in the same orientation again because this has a negative magnetic moment. So, the configuration can be easily understood in a simple diagram. I consider the parallel orientation of the magnetic moment, lowest energy possible orientation of this nuclear spin in a direction parallel to the field. This orients electron opposite it. This electron gets paired with another electron which is in the sigma bond with respect to this one, and this electron orients this proton opposite to this. I'm sorry, this carbon nucleus opposite to this. So now I understood orientation of proton and carbon. What does it? The adjacent carbon. Now, because of this type of mechanism, first Fermi contact, then Pauli principle pairing up, then again a Fermi contact. These interactions will force the neighboring carbon to have spin oriented opposite to this field. Please understand the concept now. I took initially proton to be in the direction of the field. When I went to Fermi contact, first Fermi contact, then Pauli principle of electrons getting paired. Again, this electron having Fermi contact with this carbon. Finally, because of this proton ensures or forces this carbon in a direction oriented opposite to this field. Now let us look at the orientation of two nuclear spins, proton and carbon. They are oriented opposite to each other by this mechanism. So I started with the parallel orientation of proton spin with respect to field and ended up getting carbon orienting opposite to the field by a single sigma bond. Remember, this is a concept. Why does it happen? Because that is the favored configuration. Okay. Now you may ask me a question. Fine. You took the parallel orientation. There are two orientation for the proton spin. You took the parallel orientation. What happens if I take the opposite one? That question you can ask. True. We can also work out the same way. Now you take this as a negative orientation. Correspondingly, this electron gets oriented opposite because of my negative magnetic moment I'm showing in the same direction. This gets paired with the bonding electron. This forces the carbon spin to align in a direction parallel to the field. You understand? So now, whether you take parallel orientation of the new magnetic moment of proton or anti-parallel orientation with respect to the field, it always ensures the carbon spin orients in the direction opposite to its magnetic moment. So, okay, and this type of thing, what I can say, when this type of interaction says, I am telling carbon 13 spin sees the polarization of protons. It senses this polarization. Or in other words, the proton spin senses the polarization of carbon. Either way is correct. Please remember, don't get confused. What I said, whatever the direction of orientation of the magnetic moment of proton you take, it forces the carbon adjust bonded to it by a single sigma bond in a direction opposite to it. Nevertheless, simple concept you understand, the proton spin senses the polarization of the carbon spin, which is mediated through covalent bond. And this is what is called scalar coupling, an interaction between two nuclei, magnetic nuclei which are NMR active through covalent bond. This is called spin coupling or J coupling or covalent bond mediated coupling. All these are terminologies. Please remember, this is called covalent bond mediated J coupling. Now, with this, we can understand a lot about this coupling. We'll go slowly, one by one. Many things are there for us to understand. Before I go, I'll give you some salient points of scalar coupling. Please remember them. These are all very important points. I have compiled all those things for you people to understand very clearly. Okay, please remember, these are all points I'm just like a bullet points I'm giving you. Take a note of this. Remember each and every point, it is very useful for you. And we will discuss these things later. And next 1 or 2 classes or 2-3 classes, we will be talking only about scalar coupling. Lot more of these things we will discuss. Okay. So I'll start listing one by one. First, just now I discussed, it is a covalent bond mediated interaction. It always, the spin polarization of one of the protons will go to the other spin which is interacting with this only through covalent bond. Let us take the molecule for an example. I have a CH2 group and a CH3 group. Don't go into the details of the molecular structure, whether valency is matching and all those things. I am not worried about that. I just wanted to show you something. Okay, just to see. Now, according to this statement of mine, what is the J coupling? Let us take this proton. This proton can interact with this proton through this bond. It comes to proton to carbon. Let me show you the polarization of this proton. C is sensed by this carbon. This is further sensed by this carbon, and this polarization is further sensed by this proton. See, this proton interacts with this. As because of that, both Fermi contact, Pauling principle, and then again Fermi contact. Like that, it keeps on going. So the magnetization or polarization of this proton is transferred to this carbon to this through bond, and this carbon to this proton through bond. So it's a covalent bond mediated interaction like this. You may ask me a question. What about this proton and this proton? They are nearby in space. No, there is no direct transfer of magnetization through space. This covalent bond mediated interaction, scalar coupling, has to be only through bonds, covalent bonds. If it is through space, there are examples, one or two. I'll come to that later. There are deviations like this, but majority are all the time. The rule is basic rule. Remember, it is mediated through covalent bond. This is the first point, and this is also not allowed. Now, the coupling is always denoted by N, J, I, J. N is the number of bonds separating two spins. I and J are the two interacting spins. Now we'll go back to this example. This proton is coupled to this. How many bonds are there? 1, 2, and 3. So this proton and this proton are separated by 3 bonds. And if I call this as proton X and this as Y, so what is my nomenclature? 3JXY. So these two protons are separated by 3 bonds and the interaction is between this spin and this spin. So I and J refers to the interacting spin. N tells you the number of bonds they are separated sequentially. You can't say this the proton and some other proton, and so it has to sequentially get separation. Okay, so you cannot draw a line here and say it is separated by one bond. No, you have to go through chemical bonds sequentially. So now you know what is the nomenclature we use for measuring the coupling strength between two interacting spins. It is NJIJ. N is the number of bonds separating the two spins, I and J. Okay. Now another thing, J couplings depends on the electron charge density of the nucleus and are not averaged in solution state. Very interesting thing. J coupling is not averaged out in the solution state. Remember in 1 or 2 class, first or second class, when I was discussing with you, I did say that dipolar coupling is direction dependent. It is orientation dependent. I said that gets averaged out in because the motion averaging in the solution, it vanishes. That's what I said. But I also said J coupling do not vanish. This is the reason. It depends on the electron charge density and are not average in solution state. And it does not depend on the orientation of the internuclear vector, unlike dipolar coupling. So J coupling has no direction dependence. That is why it is called scalar coupling. If it has a orientation dependence, you can call it a vector, right? So it is not direction dependent. It has no direction. It is simply a number. It is called a scalar coupling. Okay. And another salient point number 3. The strength of interaction is few hertz to few tens of hertz. Let us say the two protons are J coupled. How do you expect its interaction strength? It is always expressed in hertz. J is always expressed in hertz. Remember, chemical sheet was expressed in ppm, delta, but J is always expressed in hertz. So it can be few hertz, 10 hertz, 5 hertz, 0 hertz, close to 0, maybe 0.1 hertz to a large value. In a heteronuclear case, it can be very large also. So it depends upon the coupling strength, whether it is homonuclear or heteronuclear. If the coupling is between like spins, like homonuclear spins, there are ways we can say what is the coupling strength for 1 bond, 2 bond, 3 bond, like that. Similarly, if they are heteronuclear also we know. Remember, but one thing, the strength of interaction is always from few hertz to few tens of hertz. It can be 1 hertz, 2 hertz to several tens of hertz. Point number 4. Coupling interaction between these spins can extend beyond 1, 2 or 3 bonds. It is not always one bond. I just now showed. It can extend up to n number of bonds. See, for example, in this case, this can be it is separated by 2 bonds. With our nomenclature, it is called 2JHH. Remember. Now, what is this? It is separated by 3 bonds, 1, 2 and 3. It is 3JHH. What about this? 4JHH. This 5JHH. This 6JHH. So it can extend beyond 1, 2 or 3 chemical bonds. Of course, the interaction strength decreases. I tell you later when we go. The strength of interaction is more when it is 1 bond or 2 bonds. The same order decreases. 1 bond is larger, then 2 bond, then 3 bond, then 4 bond, 5 bond, like that. And always there are some deviations and exceptions in NMR that we will discuss later. But this is the important point. Coupling interactions between spin can extend beyond 1, 2 or 3 chemical bonds. Another point, the value of coupling can be positive, negative or 0. If I say the 1 bond or 2 bond interaction between this proton and this proton is 10 hertz. It is all expressed in hertz, I said. Coupling strength is in hertz. If it is 10 hertz, what is 10? Is it plus 10 or minus 10? Sign is important. I am telling only the magnitude is 10, but it also has sign. J coupling has a sign. So the coupling can be positive or negative, but it can be 0 also. There is a J coupling, but J coupling value is 0. See, for example, this and this, if I take this coupling may be 3 bond coupling may be close to 0, and this may be larger. Sometimes 3 bond coupling may be 0, but 4 bond coupling may exist. We don't know. It can happen. So what it means is the value of coupling can be positive, negative, or it can be 0. All are possible. Point number 6. Coupling can be between homonuclear and heteronuclear NMR acting multiple spins. Very important point. The coupling is not always between homonuclear. It can be between homonuclear spins and heteronuclear spins. For example, look at this molecule. Phosphorus and proton, there can be coupling. This is 1 bond coupling. That's allowed. Though they are not like spins, they are heteronuclear spins, proton and phosphorus. There is a coupling. And this is also possible. And look at this molecule. I am looking at fluorine. Intentionally, I have put 2 fluorines here. Now, this coupling can be there, homonuclear. This heteronuclear coupling can be there. Homonuclear coupling is between 2 protons. Heteronuclear between proton and fluorine is there. And heteronuclear between carbon and proton is also there. Homonuclear coupling between 2 carbons can be there. And heteronuclear coupling between carbon and fluorine is there. And homonuclear coupling between fluorine and fluorine also is there. And heteronuclear coupling between fluorine and proton is there. Imagine, I have got 3 nuclei here. I can get all possible homonuclear and heteronuclear couplings possible here. It's not that it is not possible. There is no rule that you should couple only to homonuclear spin. It should couple only to heteronuclear. Every coupling, so long as there are NMR active nuclear spins present in your molecule, there can be coupling among homonuclear spins and also heteronuclear spins of varied strength. It can be there. Okay, you understood now? There are so many couplings here: homo between proton, hetero between proton carbon, homo between carbons, hetero between proton and fluorine, and homo between fluorine and fluorine. All those things are possible. And coupling constant is a scalar quantity and is expressed in number. It is in hertz. It is a number. I will say coupling between 1 bond coupling or 2 bond coupling here, maybe 5 hertz, 10 hertz. I express in terms of number, and unit is hertz. It is just a number. Okay. Scalar coupling, point number 8. The magnitude of the spin-spin coupling between the coupled spins decrease with the increasing number of bonds. Very interesting point. Remember, as the number of bonds sequentially keeps on increasing, take a molecule. Now, number of bonds keeps on sequentially increasing. The coupling strength keeps on decreasing. Take, for example, one bond proton-proton coupling. This is larger than 2 bond proton-proton coupling. This is even larger than this one, 3 bond. 3 bond coupling is larger than 4 bond coupling. So it is a usual trend. Usual trend is the coupling strength decreases with the increasing number of bonds. But there can be exception. It is a trend. There are always some one or two deviations and exceptions in NMR. We will discuss that later. Now, point number 9. The coupling constants are independent of the applied magnetic field. Very interesting point. I measure the coupling constant between two protons, let us say, or between proton and carbon at 400 megahertz. It is say at 400 megahertz, coupling between two protons is 20 hertz. I go and measure the coupling in 800 megahertz. Again 20 hertz, it won't change. It is field independent. Remember, in chemical shift, what you are telling, it was field dependent. See the beauty of NMR. Chemical shift was dependent on the field, it was linearly changing. Whereas couplings are independent of the magnetic field. Whatever the spectrometer you measure, coupling will not change. Okay, it remains same. Point number 10. The splitting patterns are independent of the size of the coupling. You understand? If I say I because of this, I will explain what is splitting, everything when you go ahead further. The splitting pattern, if I say there are two peaks coming here because of J coupling, let us say positive J coupling. I make it negative. It simply changes like this. You will not be knowing whether it is positive or negative. As far as you are concerned, spectrum remains unaltered, looks identical, whether it is positive sign or negative sign. So spectrum in one-dimensional spectrum, you will not discriminate coupling whether it is positive or negative. Another thing, important point. One spin can simultaneously experience coupling with many other chemically inequivalent spins of varied strengths. Imagine I have considered one proton or one fluorine, one atom here. It can simultaneously experience coupling with all other things. Not that when I have a coupling, when this proton has a coupling with this, then it cannot have coupling with others. No, it is not allowed. Every one proton or one spin can simultaneously experience with coupling others with all other spins. Say, take for example now, proton, this proton. This can have a coupling with this carbon. This can also have coupling with this carbon, 2-bond coupling. This can have a 3-bond coupling with fluorine, 4-bond coupling with this carbon, 4 4-bond coupling with this proton, phosphorus, 4-bond coupling with this carbon, 5-bond coupling with this fluorine, 3-bond coupling with this proton, and 4-bond coupling with this carbon, and 4-bond coupling with this proton. See, this proton alone, if you have counted, you would have got 10 different couplings, assuming everything is coupled, all nuclei are coupled to this proton. You can expect 10 different couplings in this. Okay, I will again show you one by one. Remember, 1 bond, 2 bond, 3 bonds, 4 bond, 4 bond, this HP, 5 bond, and sorry, 4 bond, 5 bond, this 3 bond, this one, 10 couplings you can get. Maybe I would have missed one or two if I carefully see. But remember, what my idea was to tell you is, on one spin can simultaneously experience coupling with many other chemically inequivalent spins. In rare cases, very, very rare cases, so far I was telling you, covalent bond is a must to see the coupling. But in rare cases, you can get through space coupling like this without going through the covalent bond. That is an example of two like this, where one atom has lone pair electrons and the nuclei are within van der Waals contact. Very rarely you can see that type of things. Don't worry. Okay, that's an exception I'm telling you. Point number 12. A peak from one spin coupled to other chemically non-equivalent spins is split into multiplicity of peaks. Let us say I have one peak. It is coupled to another nuclear spin. It splits into two. But what happens to intensity? Comes down by 50-50. It is coupled to another proton. Intensity again further comes down. Coupled to another one. Again intensity comes down. But each time, each line starts splitting into two lines. Like a family tree. Like a fission reaction. 1 becomes 2, 2 becomes 4, 4 becomes 8. But one important point you must remember, the total intensity of this peak before splitting, and if you take the intensity of all these 8 peaks, it remains same. Total area of the multiplet and the uncoupled proton are identical. There is no difference at all. Get my point? Very interesting. You must remember this thing. A peak from one spin coupled to other chemically inequivalent spins split into multiplicity. But finally, the area of the uncoupled proton or the number of peaks which has been split into remains same. It's identical. And few other salient points. The multiplicity of peaks among groups of chemically equivalent spins is given by 2Ni plus 1 formula. I'll explain to you when I go further. For coupling among equivalent spins, the relative intensity within a multiple set are given by coefficient of binomial expansion are called Pascal triangle. I'll come to that later. This point again, I'll come back. I'll discuss more about these points in the next class because we cannot take too much of time because we have been allotted a particular amount of time. Within that I have to discuss, and then if it is excess, will come in the next class. So you understand basically in this class, I was trying to tell you, bring in another interaction parameter called J coupling, where I told you the mechanism of J coupling, how it is happening, and some of the salient points I gave you. These are the points to be remembered. We'll understand more about it later. Salient points, about 13 to 14 points about J coupling, I introduced to you. So we'll come back and discuss more about it tomorrow.